In this midterm review problem, we're off to the planet Zigridia, where we encounter a cart that accelerates along a surface, collides with another cart, continues up an incline, then launches as a projectile off a table and into a trash can. Uh, Really fun physics problem here that will tie together all the things we learned in this semester from some conversions, some dynamics, some kinematics. We have momentum and impulse. We got it all here. So I'm going to start breaking this problem down. In these yellow boxes at the bottom, we kind of have the intermediate steps. So as you go through these problems, we'll kind of fill in those values that'll help us get ultimately to the answer that they want, which is the distance from the base of the incline that it needs to land. So like any problem, let's start with our picture. So I'm going to draw a little diagram, what I think is happening here. You've got a flat surface, and then you got an incline. You've got this cart that's going here, and it's got this advanced propulsion system, and it's going to collide with a small cart here, and they're going to move up the incline, right? So this is going to move along. And we get this collision right here. The big cart and the little cart, they're going to collide and move together. And then the big cart and little cart together are going to launch with some velocity. And the end of this ramp down here is going to continue as a projectile and land on the ground here. And what we're trying to figure out is what is this distance away from the edge that it's going to land, right? So there's a lot going on here. We've got some information about the start, and ultimately we have a kinematics section here. We have a ramp kinematics section here, and then we have a projectile motion section here as well. So the problem kind of asks you to break it down. We can start with some free body diagrams here. Really, we have one object moving at the start. So I'm going to do part B here. We'll do the position times at the end. Sometimes it's helpful to have a sense of the numbers before we put that together. So I'm going to draw the FBD for this beginning phase right here. And they tell you something about this cart. So the first FBD is just this cart with this propulsion system on it. And we're on a surface. So we're going to have gravity. There are no other forces up and down that would affect the normal force. So we just have an equal normal force. We are getting a push to the right. That would be that applied force thrust that we're going to get from that propulsion device, and that's going to cause this thing to be an accelerating object to the right. We get a net force to the right. Then we're going to get on this incline, and things get a little bit hairy. So we'll do the incline. We've got our ramp. Oops. Zoom in here a little bit and draw a nice ramp here. We've got a ramp angle in this problem of 20 degrees. So this is a 20-degree angle. That's helpful to know. I'm going to put the carts here. They're stuck together. They're kind of one thing. And the first force I'm drawing is going to be gravity, Fg. Now gravity has some of this piece that acts down the ramp. So we have a piece of gravity that acts this way. That's Fg in the x. And this is going to be some of gravity that acts in this direction. We'll call that Fgy, and this is Fgx. On the ramp, we're going to call up the ramp the positive x, and away from the ramp the positive y. This thing is not leaving the ramp, and so that means we better have a normal force acting into the ramp. The motion is up the ramp. One of the things we don't know, we definitely going to have some friction down the ramp. And we're still going to have that applied force up the ramp from the propulsion, but we actually don't know which way we're accelerating. It's going to depend on some other factors. So we're going to figure that out later, but we do know that we're going to have to sum the forces and determine which way we're accelerating. This thing hopefully is going to get to the end of the ramp and take off, but we don't know if it's going to slow down on the ramp or if this thruster is pushing hard enough to keep speeding it up. Nonetheless, those are our forces in the free body diagram that we'll come back to later. And then step 3, we're now a projectile. So this thing launches off. There's the two connected things. And we're going to shut this engine off. I don't know if it clearly says that in the problem. We're going to assume it shuts off I think it specifically says it becomes a projectile. In fact, it does say the engine cuts off at launch, which means there are no forces on it other than gravity. All right, we don't have drag, there's no air resistance unless they tell you otherwise. And so we are now a projectile along a path that it's traveling on, and it's just FG. So we have an acceleration downward of 9.8. So those are our three free body diagrams. And now let's get to solving this problem here. All right, so let's look at step one. All right, step one is a kinematics problem. We have an acceleration, a time, an initial and final velocity, an initial and final position on this ramp. They tell you we're going to start somewhere, and I believe we go 2.6 meters. 2.6 meters to the right is where this other cart is located. So if I'm drawing this, I have 2.6 meters until the collision. And so I'm going to label that here in my table. We're going to start at rest, and we're going to be going at some speed when we collide. We don't know how long we're going to be going, and we don't know the acceleration. So we got to figure out a way to get there. Well, we know something about the forces. So we look at that free body diagram. We know that the net force on this cart has to cause that mass to accelerate, which means the acceleration is going to be the net force over the mass. And if we look at our table, our free body diagram, we know that net force is the thrust of the engine. So if I take that and divide it by the mass, I'm in good shape here. I know the mass of the cart by itself with the thruster on there was 2.4 kilograms. And we got to figure out that thrust force. Well, they give us some information about the thrust. In fact, they tell us it's 135 in this crazy unit called a zig dot rip per torque squared, right? And they say, well, this is a force unit. Remember, a Newton is a kilogram meter per second squared. So I'm going to set up a fence post. I want to get rid of zigs, and zigs we're going to go to meters. We have a conversion. I want to get rid of rips, and I want to go rips to, sorry, zigs are mass. I think they tell us we have a conversion from zigs to kilograms, rips to meters, and we want to get rid of torque, so we'll put in the numerator and get to seconds. And we want to get rid of two of them, so I got to get a squared unit. I can do that fence post twice, or I can square the whole thing, right? And I have conversions. I know that 1 kilogram is 1 zig. Oh, that's convenient. Got a randomized number here in our positive physics, and that makes that conversion pretty easy. We know that 2.4 meters is the same as 15 rip, and we know that 1 second is equal to 0.64 torque. And so when I set up this fence post and I multiply the numerator across, make sure I square 6.64 and divide by the denominator, which is 15, I end up with my applied force of 8.85 kilogram meter per second squared, which is what we call a Newton, right? So at this point, I can calculate my acceleration. My acceleration is going to be 8.85 newtons divided by the mass of 2.4. And that's going to give me an acceleration value of 3.69 meters per second squared. So I'm going to put that in here, 3.69 meters per second squared. And so now we have a fan cart accelerating, and ultimately we need to know how fast it's traveling when it collides. At this point, we have a collision. All right, and so we need to know how fast it's going when we get a collision. And when it gets there, that's going to cause a new velocity for part 2 at the beginning, at the collision. Well, V final for part 1, we don't have time, so that V final squared equation is a good one. It's equal to V initial squared plus 2A x final minus x initial. I'm going to plug in the values. I know V final squared has to be 0 squared plus 2 times my acceleration, 3.69, and times my change in position, which is 2.6 minus 0. And that's going to give me a value, and then I've got to take the square root of both sides, and I'm going to get a velocity at the end of this point. Let's pull out my calculator. We're going to have 2 times 3.69 times 2.6. I'm going to take the square root of that answer, and I'm going to get 4.38 meters per second. So that's our final velocity here. Now, we are going to graph some things, so I might as well find the time. If I know the final velocity and the initial velocity and the acceleration, well, I know that v final is at plus v initial, which means I know if I'm finishing at 4.38 meters per second with an acceleration of 3.69 meters per second squared for some time, plus my starting velocity, that means if I divide that final velocity by the acceleration, we end up with the time it took to do that, which is 1.19. T1 is 1.19 seconds. So not asked for, but we'll use that later in our graph. So we now know this cart is at this stage here where it's moving. It's got its little thruster. It now has a velocity of 4.38 meters per second. And we have this other small cart that's at rest. And they're going to have a collision. And after the collision, this big cart and this little cart are going to be stuck together, moving at a final velocity together. And when we see a collision, we think conservation momentum. The momentum before is equal to momentum after. All right, and so we can have m1 v1 at the beginning plus m2 v2 at the beginning has to equal m1 v1 at the end plus m2 v2 at the end. In this case, that means we have our mass, which was 2.4, traveling at 4.38 right before the collision, plus the mass of the second cart, which they tell you is 0.4 kilograms, but it's not moving, so there's no momentum at the beginning. And then these two masses collide, and when they stick together, those are the same velocities, which means I can add the two masses together, and they're going to be moving together at that new velocity. Right? So when I isolate this, I end up with a final velocity after the collision. You get something in the ballpark. It's going to drop. So it's going to be 3.75 meters per second. So now we get to this point where this cart is now traveling up the ramp. So we have this ramp problem here, and you have a cart system moving at 3.75 meters per second. It's going to get to the end, moving at some new velocity when it becomes a projectile launched at an angle. And we know this ramp is 0.4 meters long, and we're back to another ATVX table, right? So this is a kinematics. We're going to call, again, the x direction is now up the ramp, and we're going to have an acceleration, a time, an initial, a final, initial and final position. And let's call the bottom of the ramp 0. Let's call the top of the ramp 0.4 meters. We don't know how long it'll take. We know it's starting at 3.75 meters per second. We don't know how fast we're going to be going at the end. We don't know if we're speeding up or slowing down yet. And we're trying to find that acceleration, right? So ultimately, we need to find that acceleration. And so we're back to that free body diagram. When you look at that free body diagram, I'm going to redraw it real quick. All right, again, we're on a ramp. Oops, get my squiggly line here. Oh, this is struggling here. There we go. Let's try one more time. There's our cart. Let's just draw it as one box. There's our force of gravity. We have our piece of gravity in the y, piece in the x. We have our normal force into the ramp. We have friction acting down the ramp. And we have our applied force up the ramp. And again, we look at x and y. And what we're going to do with forces is we're going to look at all the forces in the x and all the forces in the y. And remember, the net force is equal to m times a. But because we have two directions, we're going to split it into an x acceleration and a y acceleration. And we're going to organize all the forces. So all the forces along the ramp would be my applied force from the engine, my friction, which is acting down the ramp. The applied force is up the ramp. And we're going to have sum of gravity, the piece that's acting down the ramp, the x direction, is also in the negative direction. Remember, we're calling positive up the ramp. So we have 3 forces in the x. In the y direction, we have gravity in the y, which is acting in the negative direction. And we have the normal force, which is acting in the positive direction. Right? So we have those 2 forces. Now we know the total mass of this system is 2.8 kilograms. And we know in the y direction, we're on the surface, so we're not accelerating, which means if I can find one of these forces, I know the other. I know what they have to be. Well, let's put things together here. Well, we know the mass. If the mass is 2.8 kilograms, then the force of gravity is always mass times the acceleration due to gravity. So it's going to be 2.4 times the downward 9.8. I can pull out my calculator here real quick and find that the weight, 2.4 times 9.8, is 23.52 newtons. Now that's this arrow that's acting straight down. Well, we need to incorporate that angle, right? So that 20-degree angle means we can do some trig to find the x and the y piece of gravity. And sine slides, we know that the length of the hypotenuse is 23.52, which means FG in the x is going to be 23.52 sine of 20 degrees, and FG in the y is going to be 23.52 cosine of 20 degrees. And so again, I get my calculator out. If I take that and I multiply by the sine of 20, sine slides on ramps, we know that the piece of gravity acting down the ramp is 8.04 newtons. So that's going to be my x value. This is 8.04 newtons, right? And again, I use negative as down the ramp, which is the way gravity would want to pull it. And if I take the 23.52 and I multiply times cosine of 20, you get the gravity that's into the ramp, 22.1. And that's going to be the y piece, 22.1 newtons. Right? And now that we know the y piece, since the only other force in the y direction is the normal force, we now know the normal force has to be 22.1 newtons. And we're still missing 2 pieces. Well, actually, we know the applied force of the engine. That hasn't changed. It's still pushing at, what was the engine force? We looked it up. Oh, 8.85 newtons. That hasn't changed. So this is 8.85 newtons. But again, we want the acceleration. We still are missing friction. Well, we got a bridge. We know the normal force, and we have a bridge between the normal force and friction, and that's with that value mu. And friction is always equal to mu times the normal force. And they tell you that mu is 0.27 for this surface. I'll double check my values. 0.27 is the kinetic coefficient, and we know 22.1 is the normal force. And so when I multiply those, I get a magnitude of the friction force to be 6.96 newtons. I'm going to put it right here. And now I have all 3 forces in the x direction. I can sum the forces in the x direction. I know that the applied force, the friction force, and the gravitational force in the x are the net force that cause that mass to accelerate in the x. The applied force is to the right at 8.85 newtons. Friction is down the ramp at 6.96, so I make it negative. Gravity is down the ramp at 8.04. The mass is 2.4, and I can solve for that acceleration. The net force, if I add all these up, I get negative 7.50 as my net force, which causes the 2.4 newtons to accelerate. I'll get rid of the unit so we're consistent here, times the accelerate. And when I divide by 2.4, I get an acceleration that ends up becoming negative 2.68 meters per second squared. That just means it's acting down the ramp, which means it's going to slow this cart down. And so we can put this over here, negative 2.68 meters per second squared. And with that, we can find the final velocity. We can use the v final squared equation again, we know the final velocity on the ramp squared is equal to the initial velocity on the ramp squared plus 2 times a times the change in position on the ramp. That means v final squared has got to be the initial velocity of 3.75 squared plus 2 times the negative 2.68. My final position is 0.4. I called the bottom of the ramp 0. And when I solve for v final, I get a final velocity of 3.54 meters per second. So that's 3.54 meters per second. So we lost a little bit of velocity. It appears it's not really on that ramp for very long, right? It's only going less than a half a meter. So it shouldn't take very long to be on the ramp. If I want, I can find the time. Remember, v final is equal to at plus v initial. We can find the time on the ramp. V final is 3.54 and negative 2.68t plus 3.75. I can subtract the 3.75 from the 3.54, and I get negative 0.21 is equal to negative 2.68t. That means the time on the ramp, t2, would end up being that 0.21 divided by the negative 2.68. So a really short amount of time, 0.078 seconds. Just a fraction of the time that thing's on the ramp before it launches. All right, so we're almost there, 0.078 seconds. So this cart is now at the top of the ramp. This combined cart is now traveling with some velocity. We know that velocity is now 3.54 meters per second. It's launching at the ramp angle, and it's leaving this ramp, and it's going to land on the ground down below at some distance away. They tell you the height of that table is 1.5 meters. And we're trying to find that horizontal distance that it needs to get to. All right, well, now we're in a projectile motion mode. So let's set up our XY table. A, T, V initial, V final, X initial, X final. And in the Y, A, T, V initial, V final, Y initial, Y final. Let's call this position 0, and that means our answer is going to be whatever that is. In the X direction, we need to figure out what that is. Well, let's do our trig. Remember, with that angle, that's our velocity in the X. Our Y is up. We could put it here. We see our right triangle. There's our Y velocity. The velocity in the X is going to be the hypotenuse, 3.54 cosine of 20 degrees. And the velocity in the Y is going to be 3.54 sine of 20 degrees. I'll pull out my calculator and get those values to put into our table. 3.54 sine of 20 is 1.21 meters per second. That's going to be positive 1.21. That's my velocity in the Y. And let's pull out the X. 3.54 cosine of 20 gives me my X velocity of 3.33 meters per second. Again, the X is constant velocity because we're not accelerating, and it's 3.33 meters per second for some amount of time. That time is going to be equal to the time it's in the air when it's accelerating downward, because it's the only force is in the Y. It's going to hit the ground at some speed. It's starting elevated at 1.5 meters, and it's going to get all the way to the ground. All right, so I can use the Y side to find the time. I'm going to use my position function. Remember, Y final is equal to 1/2 AT squared plus V initial t plus Y initial. I can plug in my values. 0. Half of negative 9.8 is my 4.9 t squared plus my 1.21 t plus my initial height. Hey, it looks like I got an A, a B, a C. I can find the time to get to the ground. I'm going to pull out my quadratic equation. Program quad Make sure you have this in your calculator. Negative 4.9, 1.21, and positive 1.5. And I get 2 times. One's going to be negative, one's positive. We got negative 0.44 and positive 0.69. Negative 0.44 and positive 0.69. Well, the negative time was before the launch happened. That didn't occur. So that becomes our time of 0.69 seconds, which is my x time. And now I can find my position. Remember, in the x direction, when acceleration is 0, we just get velocity in the x times time plus x initial, which means my final position is going to be my 3.33 meters per second times the 0.69 seconds, and we should get exactly 2.30 meters, and that becomes our answer. We're 2.3 meters away. So there we go. Worked our way through this whole problem here, and we found that this thing's going to land 2.3 meters away from the target. But wait, we got one more thing we waited till the end to do. I'm going to set up my position time and my velocity time graph. All right, now the way we decided to do position was to consider this whole length of this problem x. So the x direction changes. X is up the ramp, x is this way, and then x is that way again, right? And we've got 2.6, 0.4, and it looks like another 2.3. So let's call this the 2.6 point. Let's call this we're now at a full 3 meters when I add a 0.4 to it. And then let's add another little bit. Let's call this the 5.3 meter mark if we're adding up all these positions. So if I go to the collision point was 2.6 from the start, up the ramp another 0.4, and then another 2.3 away in the x. And now time-wise, the first segment, it took how long? It took, let's look at our table, it took 1.9 seconds, and then 0.78, and then the final piece was 0.69. All right, so if I'm looking at those 3 times, all right, I'm going to say this is 1.19. The second segment was just a fraction of that, was 0.08. So we're going to put that a little bit further away, and then another 0.79, which will be probably about, let's call that here. We'll just pick 2 spots. And so I'm going to start here. At 1.19 seconds, I'm located here. Another 0.08 seconds, I'm located here. And at the very end, I'm even further away. I'm located here, right? When I'm located there, here's my velocity time. I have no velocity. I'm going the fastest at this point. Right at this 1.19 is when I'm traveling the fastest. Then I slowed down a little bit. So this velocity was the first velocity, 3.75. So we'll call this 3.75. This is in meters per second. And then I slow down a little bit, not much. That value would be the 3.54. All right, and then I'm traveling horizontally at 3.3 right at that launch. We get a change in velocity again. We'll come back to marking that spot. And so for this last little bit, I'm moving at constant velocity. It kind of almost drops a little bit to 3.3, the exit value of it all the way to the end here. It's a little bit wonky because we transition from moving x up the ramp to moving x away from the ramp. That's what that little drop is. All right, so all my velocities, we're dealing with uniform acceleration, so we got lines, a little downward slope, and then instantly we're here, and then we're at constant velocity in the x direction while we're in free fall. It's a little wonky. I probably wouldn't do this on you on a test of have you change our axes here, but just wanted to get some practice drawing. For this part, we're speeding up. So we're speeding up for this part from rest, and then we're slowing down. This is going to be a little hairy. We're going to slow down, and then that should be a little downward parabola, and then kind of constant velocity to this point. These should blend together, be a little smooth. Again, I think when we change our axis, it falls apart a little bit. But at least from a standpoint of getting the concepts of these graphs. I should see curved up, we're speeding up, curved down, we're slowing down, and then straight line, we're continuing at constant velocity. And again, at this point in the graph, our x-axis is changing direction again, which is why the velocity is a little bit wonky there. But hopefully it gives you a sense of a full problem here. Again, we've tied it all together, right? We've got dynamics with forces, 3 different types of scenarios. Kinematics, speeding up. A collision, conservation of momentum. We've got a dynamics on a ramp to find an acceleration where we're slowing down. Another kinematics to figure out a velocity at the top of the ramp. And then a nice projectile motion angled launch problem here at the end to find that total final position, and a little bit of graphing here. So if you can navigate this problem, you are ready for this exam. If you got any questions or if you found any mistakes, let me know. You can solve this problem with some randomized numbers here in positive physics to get yourself some practice. But this is really the ultimate litmus test on whether you can put everything together this semester. Best of luck to you.